All right. Hello, folks. Welcome back to Start 445 Regression Analysis. I hope you're enjoying the course so far. Um, this lecture is going to talk more about inference issues, and we introduce indicator variables. But before then, you've seen that most of my examples are replete with the logarithm of the dependent variable or logarithm of the dependent and independent variables. So in this lecture, I want to spend some time to derive to you why we interpret them as percentage changes. I'll do for one, and the other one, I will just explain to you how we do it. Okay, so take for example, if we have, just a second, let me grab my pencil. So if we have ln of y is not different from beta 0, for example, plus beta 1 x. So as you can see, my y is logged, but my x is not. So I am arguing that, how do we interpret beta 1? So if x changes by 1 unit, okay, y changes by 100 times beta percent. So you multiply the beta 1, I beg your pardon, is beta 1. You multiply the beta 1 by 100 and say when x changes by 1 unit, y changes by beta 1 times 100%. That is what I want to derive. Okay, and so when you see log of the dependent variable, that's the interpretation. And I'll show you if we have log how to interpret, pretty straightforward. Okay, listen to the language carefully. Listen to me carefully. Okay, pay rapt attention. When x changes by 1 unit, all of ln of y will change by beta 1. That you are familiar with. But I am not talking about all of ln of y. I'm talking about only y. That's the distinction. You are familiar with the fact that if x changes by 1 unit, this whole dependent variable ln of y changes by beta 1. But I don't want to talk about ln of y. I want to talk about just y, which we are interested in most of the time. Okay? Therefore, I want to show you that if x changes by 1 unit, y will change by 100 times beta 1%. Okay, let's do it. I'm going to use this symbol, the delta, to mean derivative, to differentiate, okay? So this, when you see this, I mean I'm differentiating. Therefore, my dear friends, what is the derivative of ln of y over the derivative ln of y, differentiating ln of y with respect to x? This is a constant, it has no x, it goes to 0. This becomes beta 1. And then this also, okay, goes to 0 with our assumption. Okay, what does this mean? Remember, if you are differentiating ln of something is what? Differentiate the variable and divide by itself. Okay, when you differentiate x with respect to x, you get 1, and this is x. That is why the derivative of ln of x is 1 over x. The derivative of ln of x, differentiate the variable with respect to x and then divide by itself. That is what will come to play here. The derivative of ln of y is the derivative of y divided by itself. Okay, and then we have our change in x here. Once again, if I want to differentiate z with respect to x, dx, okay, I will differentiate z itself with respect to x and divide by the z. That's the idea. Differentiate x, ln of x, to differentiate ln of x, differentiate this x with respect to x, you get 1, and you divide by x itself. So over here, to differentiate ln of y with respect to x, you differentiate y, okay, with respect to x, and you divide by y. I'm not writing the respect to x, but basically, the delta here means differentiate with respect to x, okay? So I'm differentiating y divided by itself, and I have my delta x here. And this is equal to beta 1. Let's cross multiply, okay? Then we have change in y over y. It's not different from beta 1 times change in x. Now from here, as you can see, this thing here, it looks like changing y over y. So immediately I multiply by 100, then I get a percentage change. So I'm going to multiply both sides by 100. Change in y over y times 100 is not different from beta 1, 100 times beta 1 change in x. I've multiplied both sides by 100. So nothing changes. Therefore, just a second. Therefore, this is a percentage change in y, right? If you do commas, you know change in y over y times 100 is percentage change in y. Percentage change in y. And therefore, this is what equals to 100 times beta 1 change in x. Therefore, that is the interpretation. When x changes by 1 unit, okay, there will be 100 times beta 1, okay, percentage change in y. If x changes by 1 unit, then there is the percentage change in y is 100 times beta 1. You will see its application surely. Okay, excellent. I hope you are following so far. Let me share the slides and then we proceed. Now, back to what I want to do for this section. We are talking about further issues with regression analysis. And here we will introduce things about polynomial regression and later on, okay? So, for example, if I estimate wage, okay, we believe that people's wage depends on their experience, and the experience will increase with age, and then it may no longer be useful, okay? As your experience increases, your wage will be increasing, but we believe it will plateau, okay? It will plateau, which signifies a quadratic structure. And for that reason, the researcher believes he must add experience squared to capture the curvature that experience will be increasing your wage up to a time it might not matter anymore. So whenever you believe that your graph or your variable has this structure, you can introduce a quadratic. Of course, it shows this structure. You want to add power 3 and so on. Okay, now it is settled in economics or in the literature. I know that if I'm studying people's wages, I must add experience and experience squared and so on. So how do I know I will add a square or cubic? The literature will guide you. Once you read around before you frame your research question, you will know. And remember, as young researchers or even researchers, you are working within the domain of existing research and so on. So that should not be an issue. So this has been estimated, okay? The key point is that the effect of experience on wage, please pay attention, the effect of experience on wage is not just 0.298. No, there's another experience variable here. So always, you must differentiate before you can see the impact. So the derivative of wage with respect to experience is what? 0.298 minus, you differentiate this, right? So the 2 will come down here, this and that. You reduce the power by 1. So what does it say? That the impact of experience on wage depends on the experience variable itself. So this is how we interpret it. Pay attention. How much of this variable do you have in existence? You plug it in there and that's it. So most of the time, because the impact of experience on wage even depends on how much of experience that is available or from the starting point, we would sometimes add something like, we'll sometimes plug in interesting values like the mean of the experience X bar, the lower quartile, upper quartile, or the median. And then we'll say, oh, the impact of experience on wage at the average level of experience is this. You plug in that number here. Okay, so there should be no confusion. That's how we treat it. You must differentiate the variable, dependent variable with respect to the independent, before you can think about the impact. Okay, in our linear example like this, we often did not differentiate and quickly knew the impact is beta 1, because even if you differentiated, it boiled down to beta 1. So here, it's not suicidal to just look by inspection and conclude that beta 1 is the impact of X on Y. But once the variable is repeated, you have to be careful. That is my story for this morning. Okay, so because we have a quadratic term and we were arguing that experience will increase your wage and it may plateau later on, people will ask you during your presentation, what is the turning point? And then from our calculus, remember, dy dx is equal to 0. And this looks like the dy dx, you set it equals to 0 and solve for experience. That gives you the turning point. Okay, so on the next slide, we have it here. Okay, this looks like you should be able to tell that, right? If you set dy dx equals to 0, this is what you have. Okay, if you have y is equal to beta 0 plus beta 1x plus beta 2x squared plus u, then dy dx will be what? Beta 1 plus twice beta 2x equals to 0. So if you solve for x, the stationary, okay, the turning point x star will be what? Negative beta 1 over 2 beta 2. So that is the idea of what you are seeing here. And because x as experience cannot be a negative number, we take the absolute value and so on. So people will ask you, what is the turning point? So you will have this number, beta 1 would have been estimated. This would have also been estimated. In your homework too, I've challenged you to learn the estimation. So this is known, you plug them in and you get a number like this. But we are saying that be careful not to say the turning point is 24.4 years of experience. That's what we are saying here. After you find it, when people ask you the turning point and you find it, just be careful. It may not be true, right? If you have only few data values here, then it's not a good idea. Unless you have a lot of data points, plenty people in the data have experience greater than 24, then it makes sense. Okay, but if you just have your sample, in your sample, only 2 people or 3 are having experience more than 24, then it's not really a turning point. It is completely irrelevant. Okay, so you don't dwell on it. You say, well, I calculated a turning point, but it's not so useful because only 10 people have experience greater than 24, and I don't think the model is actually capturing that. Okay. Okay, so this slide is showing you that we can have more sophisticated models. You can have log of x and then you square it. The key here is that do not include log x and log x squared, because this one is the same as what? 2 times log x, using the laws of logarithm. And therefore it becomes perfectly collinear with this guy. And therefore it violates the assumption of no perfect collinearity. Instead, you must square the whole of the log x. You must square everything if you want to include a square of a log term, and not just squaring the x itself. So pay attention. And here we differentiate to show you the impact depends on log of nitrogen of x, okay? And there are other possibilities where you can include a third power and so on. These are higher powers. They are all allowed in regression as long as you believe it will capture your regression. Again, this is a linear regression model, although it captures some curves just because it's linear in the parameters. Okay. So let's take another example here. The price of a house being sold depends on the square feet, okay, the space in the house and the bedrooms, okay, or this is actually this is the number of bedrooms and how the size of the bedrooms. In other words, okay, so additional terms have been added, okay. This is, okay, so we are talking about interaction terms. So as you can see, there's square feet here, bedroom, and an interaction of square feet times bedroom, and then a 4 variable bathrooms. What's the idea of interaction terms? When you believe that the impact of one variable depends on some other variable, you interact them. Okay. When there are many bedrooms in a house, people like it, the price is high, but it doesn't have to be small bedrooms. So the impact of the bedroom also depends on the square feet, the size of the bedrooms. So you interact them. That's the idea of interaction. So that you can probably capture the impact of the bedroom on the price of a house. Okay, so let's say the impact of free SHS on core mathematics score. This is core mathematics score of students. The core mathematics score of students, we want to see the impact of free SHS on the core mathematics score of students. So beta 1, whether the student enjoy free SHS or not, plus U. Then somebody say, oh, no. I think the impact of free SHS depends on whether the student is a boarding school or a day student. Whether he's in a boarding school or he's a day student. Then we have to include this term. Okay. Then we have to include whether the student beta 2 is a day student plus beta 3. Then you interact them. Free SHS times whether he's a day student or boarder. So this, once you interact with two variables, it's normal practice to include them individually. So here we've corrected the model that the impact of free SHS on core mathematics score actually depends on whether the person is a day student or a boarder. So this variable is supposed to, this day variable is supposed to take a value of 1 if the person is a day student and 0 if he's a boarder. Later on, I will talk about these are called indicator variables later on in this lecture. So that's the idea of interaction terms, okay? Now, beta 1 over here, beta 1 is not the, or beta 2, sorry, I'm interested in beta 2. So beta 2 here is not the impact of bedrooms on price. The impact of bedroom on price, you must differentiate. The price, the bedroom, then you get beta 2 plus beta 3 square feet. So the impact of bedroom on the price of the house depends on the space, the square feet, okay, available of the bedroom or the house, okay? Let's think about square feet as the space in the house, basically. Okay, only when square feet is 0 do we have beta 2 as the impact of bedrooms, okay, on a house, the number of bedrooms on a house. Okay, more on goodness of fit. Our R squared measures what? How the regression was able to explain, the regression model explained variation in the Y variable. Remember, a high R squared does not imply there's a causal interpretation. I've talked about causality already. And a low R squared does not make the model useless. It could still be useful for estimating the parameters, okay? It is when you are predicting something that the high R squared is usually useful. Sometimes you just want to get a beta 1 hat, precisely estimated, low variance, and then you move on, okay? It may come with a low R squared. It doesn't mean the model is useless. I can talk more about this in class. Okay. So there is something called adjusted R squared, which is computed by our usual R squared, but you divide the error sum of square by its degrees of freedom and the total sum of square by its degrees of freedom. It's because each time you add an X to a regression, the R square artificially goes up, even if the X you are adding is useless. To penalize for adding irrelevant variables, the adjusted R squared will only go up if that variable makes sense or if it is contributing to explaining the variation in Y or the dependent variable. Okay, so this is supposed to penalize those who are fond of throwing in any irrelevant variable just to have R squared to be high, and then they run to town and say they have a good model. So the adjusted R squared will divide by the degrees of freedom. Okay, so if you are adding more regressors, then the K will go high. Okay, and then n minus k minus 1 becomes small. Once the denominator is small, this thing here becomes big. Once the whole top becomes big, 1 minus a big number becomes 0. So adjusted R squared will come down, thereby penalizing you. So that's the essence. So most people would rather read adjusted R squared than to rely on R squared, because R squared artificially goes up even when you add any variable. There is this relationship between adjusted R squared and our usual R squared. Okay, I have shown you how adjusted R squared looks like, and the R squared doesn't have these divisions. So why don't you work through the math and show that you can manipulate your adjusted R squared is to look like this? Okay, try it. Okay, or you can ask the TA. It's good practice to try these things. These are things I can ask you on quizzes or class tests. So all these things, derive them, show them. If you get stuck, come to the office hours or ask the TA. Okay, some further issues on adjusted, using R squared, adjusted R squared. Because we tend to like a higher adjusted R squared on R squared, we are saying be careful when you are comparing. For example, in this model, adjusted R squared is just what, 1 to 2%. So the model explains 2% of the variation in salary. And here the model explains 27%. You may be tempted to say you prefer this model. I prefer to run log salary on sales and return on equity. I prefer this model to this model because this model explains 27% and this model explains only 2%. We are saying you are wrong because you are not explaining the same thing. Here you are explaining just salary. Here you are explaining log salary. There are two different things you are explaining. So you cannot just choose one of them. Compare apples to apples. Now, log salary has a lot of variation in it. The total sum of squares is 391 million, making it difficult for just these two variables to explain more variations in the salary. But log salary has a very tiny variation. The sum of squares is what? 66.72. So it is easy to punch into this sum of square and explain up to 27%. It is easy to explain 27% of this number. And this is 391 million. This is difficult for these two variables to explain a significant portion. They ended up being only 2%. So you are not explaining the same total sum of squares. So be careful when you are choosing between or amongst models using adjusted R squared. That is the point. Okay. Now let me move to our qualitative or quantitative variables. Regression analysis most of the time will employ quantitative variables, but sometimes it is so necessary to control or study the impact of qualitative variables, such as gender. Gender is not quantitative, male or female, race, the industry, your region of origin, whether from Ashanti, Eastern, Volta, Northern, and so on. Or a rating, okay, or the rank of university lecturers. How do you incorporate indicator variables, as we call them, or quantitative variables? Okay, indicator because they can take 1 or 0, or 1, 2, 3, some ratings, and so on. How do we incorporate them in our model? Okay, let's first talk about a single dummy. We call them dummy, okay? Economists will say dummy variable, statisticians will say indicator. It indicates whether you are a male or female, whether you are black or white, whether you are in education industry or mining or oil, whether you are from Ashanti, Greater Accra, and so on, and your ratings. Okay? Okay, so let's keep going. Assuming we have wage is equal to beta 0 delta female, we want to see whether the wages of male are different from those of females. Okay, so that's all plus beta 1 education. How do you interpret delta 0? It is the wage gain or loss, depending on whether it is positive or negative. That's why we are using gain or loss. It is the wage gain or loss if the person is a woman rather than a man. holding other things fixed. So here, the female variable is defined. Okay, actually, it's not a good practice to call this female. It's better to call it gender. But we are calling it female so that we know that this thing takes a value of 1 if a person is a woman and 0 if the person is a man. Okay, so if you have, for example, your data in Microsoft Excel, and we have names and gender. So if you have Godwin, and let's say Amma, then because of the way this is defined, by the name Godwin, they will put 0 because I am a man, and Amma is a female 1. So this is how the data will look like in Microsoft Excel, and they will put the value there for everybody. By the way, this is called female and not gender, but I prefer to call it gender. Okay. You can actually change this to male. You can change it to male and say all the males will take 1, all the females will take 0. It depends on you. And then you plug the variable in your regression. Okay. Because the 1 is for women and the 0 is for men, the one that takes the 0 is called a base category. It's called a base category. And you compare the one which takes a value of 1 to the base category. So because 0 is for men, everything here is being compared to men. So I will say that female make delta 0 more than men, because men is the base category. So look at the description again. The wage gain or loss, if the person is a woman rather than a man, then you say holding other things fixed, as we always say. Okay, so this is the idea. Remember the equation there was what? Wage is equal to beta 0 plus beta 1 female plus beta 2, their levels of education. Let's write the equation for men. Wage is equal to beta 0 plus beta 2 education. I didn't write anything like this there because for men, this female variable is equal to 0. So this drops off. Now for women, oh, sorry, this is delta 0, right? Let me correct that. So this goes to 0 for men because the variable female is defined to be 0 for men. Now for women, let's write it out. Wage equals to beta 0. Now we have delta 0 because the value female, the variable will take a value of 1 for women plus beta 2 education. So the intercept becomes double for women, but beta 0 plus delta 0. So you see, the intercept is different for women and different for men. So that's what we have here. So this is the intercept for men, beta 0, and the intercept for women. Now, although this has 2 components, this plus that, it is still lower because delta 0 will turn out to be negative. So this value will be at a lower level than the beta 0 for men. That is why the men is on top. The line of the men is above the line of that of the woman, because this beta 0 plus delta 0 will be smaller. Delta 0 tends to be negative. Okay, in quotes, it suggests women are discriminated against, but not necessarily so. So that at the starting point, men, okay, are making high from the intercept than women, holding even the level of education the same. So that's the idea of the dummy or indicator variables controlling for gender. Okay. Okay, over here, what do we have here? Okay, it is a warning that do not add 2 dummy variables to the same model. Don't define female is equal to 1 for female women and 0 for men. Put it in a model and come and define another one that this is equal to 1 for men, 0 for women. You run into what we call the dummy variable trap. It will cause collinearity. That means the variables will sum up to 1, which we don't want. Okay, you have a name, Godwin and Amma. Then you have two variables, male and then female. So over here, Godwin will take a value of 1 and Godwin will take a value of 0 here. Here, Amma will take a value of 0 because she's a female and take 1 here. You see? So consistently, if you sum these two numbers, it's equal to 1, equal to 1. Throughout, they will all be equal to 1, 1, 1, 1. So you are summing two variables, they are equal to 1. That's perfect collinearity, which we have assumed we don't want. So that is what we call a dummy variable trap. You must drop one of them. Either you define for females or for male and choose one and run. So over here, the base category is men because men are taking a value of 0. The base category is for women. Women are taking a value of 0. So remember, dummy variable trap. And it is actually the reason why we leave out the base, one of them, okay? So for example, if you have to include January up to December, a dummy variable for all of them. There are 12 months. You want to control for monthly effect. You must leave one of them out. Let anyone you choose, like December or January or whatever. Then you compare your results to December. So you have 11 dummy variables representing January up to November, and you leave one out, like December, and you compare your result. Okay, so if you estimate something like beta 1 had January, then it means January sales, for example, are beta 1 more than December. You compare all of them to the base category, the one you left out, like December. So you always leave out one of the categories to avoid the dummy variable trap. There will be another example. Okay, if you are doing days of the week, you must leave one of the days out. If there are 7 days, you create dummies for only 6 of them, and you leave one out as a base category. Okay, so what do I have here? Oh, this is an estimation of the female and the gender and the wage equation. So they included a gender variable, education, experience, and tenure. Tenure is how long you've been with your present employer. N is 2526, R squared is 0.364. You see the female variable is negative. Does that mean that women are discriminated against? Not necessarily so. It's possible that being female, okay, actually may mean that you may not be productive, okay, as men, okay? Apologies to all the feminists. It may not necessarily be discrimination. It's possible that women are not, for example, children are not as productive as adults. So if you realize there's a negative thing attached to children, it doesn't mean children are discriminated against just because they are young. It's possible they are not as productive as they should be. So be careful that a negative here doesn't just mean women are discriminated against. Of course, there's discrimination in the US, okay, by gender and so on. Okay. Last example, and I'll bring this lecture video to a close. This is it. We are using dummy variable for multiple categories. Okay, let's define membership in each category by a dummy variable. And you leave out one category, that becomes the base category. Okay, so there are 4 kinds of people: married men, married female, single female, and single men. But we have to leave out one of them, the single men. And whatever we do, we compare it to the one we left out, the single men. You must leave one category out to avoid the dummy variable trap. So look at the interpretation of this, and then I'll be done. Look at the interpretation. When this model was estimated, because this is logarithm, remember I showed you earlier at the beginning, you must multiply this by 100% and talk about it as a percentage change in wage. So look at this. Holding other things fixed, this variable is married female, right? Married woman. So married woman, and you multiply this by 100%, 19.8% less than single men. single men is the category we left out. Okay. So here, married men make 21.3%, 21.3% more because of the plus, more than the base category, single men. Single female, multiply this by 100. So you get 110% less than single men, and so on and so forth. Okay, let me show you how the data will look like in Excel. Okay, I hope you can see Microsoft Excel. So assuming we have 4 people, Amma, her wage, John, his wage, Perpetua, her wage, Cynthia, her wage, and education variables over here. So let's say Amma is not a married male, so this place she will take 0. Amma is a married female, so 1. She's not a single female. John is a married man, so here will be 1. And he's not a married female, he's not a single female. Perpetual is a single female, so 1 over here, 0s over here. And then Cynthia is also what? Married. No, she's not a married man. She's a married female and not a single lady. Okay. So over here, we leave out a single man. Okay. That way we avoid the dummy variable trap. Not all of them will add up to 1. This adds up to 1. This adds up to 1. But you may have somebody like, let's say me. My wage is known, education is known. Am I a married male? No. Am I a married female? No. Am I a single female? No, because my category was left out. So you don't have all these variables summing up to 1, summing up to 1. No, in some places they sum up to 0. So you avoid a perfect collinearity and so on. Okay, so I'll bring this meeting to a close. Thanks. I hope you are enjoying the course so far. Please do the homeworks and so on. Let me know if you have any questions. Thank you.